Modeling is arguably the most important part of a simulation study. Indeed, a simulation study is as good as the simulation model when it follows a specific procedure based on correlated steps of an iterative loop. First step, problem formulation. Once identified a problem, you may select the bounds of the problem or a part thereof to be studied, to formulate the problem as precisely as possible. Practically, you should define the overall objective of the study and a few specific issues to be addressed. Define quantitative and qualitative criteria on the basis of which different system configurations will be compared and ranked. Formulate hypotheses about system performances. Decide the time frame, because, as we said before, it's important to understand if the model will be used for one time or over a period of time on a regular basis. Second step, collect data on system specification, input variables, as well as performances of the existing system. Identify sources of randomness in the system, for example, stochastic input variables, to analyze the data model, and then select an appropriate input probabilities distribution for each random variable and estimate corresponding parameters. Third step, develop the model according to the previous steps. Fourth step, verify that the simulation model executes as intended and then validate the model comparing its performances under no conditions with the performance of the real system. In case some barriers limits the model validation, the iterative loop allows to come back to previous steps for tuning the model and then pass the verification and validation. Fifth step. During this step, the model will be performed and optimized according to the previous results in order to conclude the procedure. Sixth step. Finally, it's important to document objectives, results, and all the procedure in detail, to sum up the process and to have the whole data for further implementation. After the overview on the basic concept of modeling and simulation and how to perform it through an iterative procedure, let's try to apply those concepts to the construction sector. Practically, it means to consider a building as a complex system composed by two models, the building model and the plant model. Those are the two parts which constitute the system, object of our investigation during a simulation modeling. So, as described in the simulation procedure, both building and plant models should be defined and modified according to respective variables such as building performance, energy requirements, and plant operation strategy for the building model, and plant performance, energy consumption, and control strategies for the plant model. With the expanding interest in energy-efficient building design, building energy simulation programs are increasingly employed in the design process to help architects and engineers determine which design strategies could be the most effective to save energy and at the same time also be cost-effective. Moreover, the construction industry is facing with the urgent demand for more energy-efficient buildings and the challenge to ensure that the energy performance predicted during the design is achieved also once a building is in use. For this reason, energy modeling simulation is considered a decision aid tool along the entire life cycle of a building, both for new and existing ones. Hundreds of different tools have been developed and they are available on the market. Some of them focus on a certain components or requirement, such as envelope, acoustic comfort, or the lighting, for examples. Or some other may simulate the whole building energy consumption. So, considering the multitude of software available in the market for the construction sector, how to select the most suitable for my modeling simulation goal? As just anticipated, tools may focus on certain part of the system, the building model, the plant model, or both. So at this link, the International Building Performance Simulation Association provides in its website a very interesting and updated list of the most currently used tools. This software listing is a valuable support for choosing simulation software because it also allows to filter your results according to the software capabilities. So you may choose a tool for simulating the whole building, or you may need to focus only on load calculation or building automation, and so on. We are quite at the end of this lecture and it's time to sum up benefits and pitfalls of simulation. Despite some shortcomings related to computational complexity, numerical approximation and result certainty, modeling and simulation are the best tools we currently have in support of reaching beyond current frontiers. Like the microscope and telescope help us to observe things not accessible to the naked eye, computers are providing us with the power to solve mathematical challenges, describing the scientific problems in a way not doable without them. They are extending our abilities with some benefits like the following, for example. The possibility to test hypotheses or new systems for feasibility. We can compress or expand time for investigation. We can perform bottleneck analysis to better evaluate system variables, and what-if questions can be answered about the real world. Of course, from the other side of the coin, some pitfalls should be kept in mind. Sometimes it could happen to fail in identifying clearly the objectives, or to collect good data for developing a good model. In general, building modeling requires spatial training, and sometimes even dedicated courses are not enough, because time and experience are often the best teachers. Consequently, simulation modeling can be time-consuming, and the hardest part often is related to the simulation results interpretation. To conclude the lecture, I would like to thank you for the attention, and I want to leave you some case takeaway before starting modeling. The presented overview on simulation definition and procedure will guide and enable you, step by step, to build your energy performance building model incrementally. So, my first suggestion is start with a specific question. You are essentially running small experiments as you design. What will happen if, and is my expectation correct? If you start with a specific question like this, the analysis will be more manageable than if you try to deliver high performance all at once. Second, be an efficient modeler. You don't have to model everything to answer a specific question. Often, building a quick study model off to the side of a representative floor or a typical condition, for example, it's a fast and easy way to inform the refinement of your design. And in parallel, choose the appropriate simulation tool according to your project goal. Finally, work to gain insight, not to replicate the final build condition. Use analysis to compare options and refine your overall strategies rather than to assess the final performance. With practice and experience, you will be able to increase the complexity of a model iteratively. That's all. and thank you for attending the lecture.